When people hear about the Great Pacific Garbage Patch, they usually picture a dense, floating island of trash you could practically walk across. But if you were to fly over the center of it right now, you would look down at miles of pristine, empty blue water. This map shows the actual boundary of the patch. Spanning the ocean between Hawaii and California, this accumulation zone covers 1.6 million square kilometers. That is a footprint 3 times the size of France. Within that massive expanse of ocean, there is an estimated 100,000 tons of plastic drifting near the surface. That sheer weight doesn't come from intact soda bottles and milk jugs. It is made up of roughly 1.8 trillion individual microscopic fragments suspended in the water. A singular concentrated mass would be a manageable cleanup target. Instead, we face a vast, nearly invisible suspension of debris spread throughout the upper water column. Researchers know exactly where this debris field lives. Driven by seasonal, converging ocean currents, the mass orbits at a relatively stable position around 32 degrees north and 145 degrees west. We have been mapping and measuring this zone for decades, yet the mass shows no sign of naturally dispersing into the wider ocean. This graph shows microplastic concentration over time. The data forms a steepening exponential curve, showing plastic concentration is accelerating every year. This aggressive curve completely breaks standard models of oceanic dispersal. The material becomes more concentrated, even as it orbits the Pacific. The GPGP acts as an active, one-way accumulation engine. There is a severe mathematical imbalance here. Far more plastic is entering this specific zone than is ever leaving it. It is commonly assumed that ocean plastic primarily flows out of heavily polluted coastal rivers and sweeps out to sea. The data specific to the GPGP suggests otherwise. Between 75 and 86% of its mass originates directly from offshore fishing activities. This material consists of highly durable polyethylene and polypropylene, discarded as fishing nets and ropes. These are industrial-grade synthetics built to survive the harshest conditions. Because of their specific buoyancy, these polymers remain suspended in the top few meters of the water column. They are just light enough to stay afloat, which prevents them from forever sinking to the seafloor. This turns the patch into a site of industrial containment failure. Heavy-duty polymers are being injected directly into converging currents that keep them tracked indefinitely. Once these specific polymers enter the gyre, they enter a state of total persistence. They do not biodegrade or dissolve in seawater. We have forensic proof of how long they survive. This plastic crate was recovered after floating in the patch since 1977, yet its structure remains entirely intact. Consumer electronics show the same suspended animation. This Game Boy shell from 1995 has spent decades in the Pacific without losing its form. This chart contrasts the total mass of the patch with the total object count. By mass, 92% of the debris consists of large objects over 5 millimeters. However, 94% of the individual pieces are microscopic microplastics. Trillions of fragments account for almost none of the weight, but nearly all of the count. The plastic is not leaving the ecosystem. Rather, UV radiation and wave action are grinding these large objects into trillions of highly toxic, uncatchable microfragments. At the surface level of the patch, the accumulation engine has reached a tipping point. Plastic fragments now outnumber natural food sources by a ratio of 180 to 1. Plankton and these transparent arrowworms physically ingest these fragments instead of actual nutrients. The particles can easily block their delicate digestive tracts, starving them from the inside out. Beyond the physical blockage is a chemical danger. 84% of these floating plastics carry persistent bioaccumulative toxic chemicals. This pyramid shows the process of bioaccumulation. These toxins act as microscopic sponges that transfer into and multiply within the fat and tissue of the predators that eat the plankton, concentrating the poison as it moves up the food web. The GPGP has become a factory for a toxic food supply. It shatters industrial waste into poisoned, bite-sized fragments that travel directly up the food chain to human populations. Because the patch is fueled by offshore industrial waste, simply cutting off land-based river plastic will not stop the accumulation. we have to actively intercept these large macroplastics and ghost nets now. Removing this mass is the only way to stop the shattering cycle before these objects can break down into trillions of microfragments. Solving the problem for the next generation requires a different approach, engineering plastics that can't shatter into persistent fragments in the first place. Scientists are developing engineered living plastics. These materials are embedded with bacterial spores, like the ones shown here, that are designed to self-destruct the polymer structure when activated. This process reduces the material to its basic building blocks in a matter of days. It essentially bypasses the microplastic shattering phase entirely, ensuring the plastic never becomes part of the bioaccumulation loop. Ending the Great Pacific Garbage Patch requires two physical interventions: a massive mechanical extraction of the historical backlog and the total removal of molecular persistence from the plastics we create in the future.